So we have a torque in equilibrium problem. Pause the video right now, digest this problem, think about it, sketch out a picture of what's going on. That's going to be critical for every torque problem that you do. Translate it from words into a picture. So here's my picture of what's happening. We have the 44 kilogram child and the 44 kilogram child and the 30 kilogram child. They are each exerting forces, which will actually become relevant. This is mostly about torque, but we're going to use forces at the end as well. So yes, they are each exerting forces, but they're also exerting torques, and we're going to figure out what the torques are. So we had highlighted the fact before that for this to truly be in equilibrium, it's not enough to say that there is no net force. It is true that there's no net force, but we're also saying that there's no net torque. The way that I like to express that is like this. I like to write that the torques clockwise equal the torques counterclockwise. You will probably be in the habit of writing that down for virtually every equilibrium problem that you solve. And over here I'm just mentioning this is the same as saying the sum of the torques is 0. We kind of did this in the two-dimensional momentum problem when we said that, you know, this is kind of like saying the vertical component of one momentum is equal to the vertical component of the other momentum in that glancing collision problem. So I like to, for every torque, I like to go in and write that. I like to write RF equals RF for every torque. And that is not a T, that's like, I like to think of it as kind of half of a pi, meaning pi, pi, the Greek letter. So that's some lever arm, some moment arm times its corresponding force, etc. And now I plug numbers in. This is a nice, easy example, and you may be wondering, well, what about the weight of the beam? The weight of the beam is technically in there, but the weight of the beam is exerted directly at the pivot, so it has no torque. Because the R for the weight of the beam, and I'll draw where the weight of the beam would be. The weight of the beam would be right here. But as it is, the only forces I really care about are this downward force and this downward force. And I'm sort of drawing those to scale. I'm drawing these to scale because the 44 kilogram force is larger, and so it has to be closer to the pivot. Okay, so obviously I took a mass times g here to get the weights, and you simply solve for R2, and it's 1.91. That makes sense. Sum of the torques is 0, but it says also find the force that the pivot must support. This would be the force that's upward from the pivot. Question?
In these seesaw problems, are there always going to be a 0 net torque?
Yes. We're never, the question was in these seesaw problems, is it always 0 net torque? Yes, because the general theme for this whole unit is we're talking about equilibrium situations. So this whole unit is static and equilibrium, so we're not worried about acceleration. Now, the answer to the force from the pivot is actually really ridiculously easy in this particular problem. In other problems, it's not going to be easy. So with a really simple problem, I'm going to show you the structure for how you should approach that. The same way that we said that there's no net torque, we're going to say that there's no net force. And the way I like to put that is that the forces up equal the forces down. So forces up equal forces down. We could also say we could also say for other problems, forces to the left equal forces to the right. The total of the forces to the left equals the forces to the right. We don't need to worry about that for this particular example, so I'll delete that. But when we do other problems, we will have to worry about that. Jocelyn?
I was going to say, do we always use 9.8 for torque?
That's just G, so 10 or 9.8. In this case, it doesn't matter because they'll cancel out. But so now you simply write down that the force is the force from the pivot is an upward force. But be careful. Now we do care about the weight of the beam. The upward force is this force here, which is from the pivot. This force here is from the pivot. This is the force weight of the seesaw, and then we have the force weights of the individual kids. So we simply plug all those in, and we have a really easy solution for this particular problem. But what's not going to be easy later is when you're trying to figure out what the left and right forces are at, say, a hinge.
Hi, David. Hey, Dave.
All right, any other questions? Any other questions?